So, we've taken a look at our 6 basic trig functions. We know a little bit about how they work in terms of right-angled triangles with those ratios of side lengths, and then we also have connected the sine and cosine functions over to the unit circle, which is really helpful. And remember, once we have the sine and cosine functions figured out, we have pretty much the rest of the trig functions that we can think of in terms of sine and cosine. So we can get tangent by thinking about the sine function divided by the cosine function. And then all the other 3 trig functions are reciprocals of sine, cosine, or tangent. So we have this idea about what these functions are, but what we haven't done yet is taken a look at what the graphs of these functions look like. You probably know a bit about what the graphs of these functions look like, so I'm going to just kind of go through this quickly. We'll take a look a little bit at the graphs of sine and cosine. They should look relatively familiar, but we'll keep an eye on some key features and things like that. Then we're going to talk about period and amplitude. I think we've talked about period and briefly what it is, at least in the last video. I'm going to get more in detail about what the period is specifically for the sine and cosine function. We're going to talk about transforming those functions. So I do have a bit of a recap up on our Canvas site of just general transformations of functions that you can go over. And then we're going to look at different variations of the sine and cosine functions, and then we'll see if we can use those to model different periodic phenomena. So lots on the docket for today, but here we go. First, what we want to do, we're going to go all the way back to our very basic way of graphing functions. We're going to take a look at these x values, and we're going to find y values for the sine function and for the cosine function. So if you want, you can go back to your unit circle. I'll just draw it real quick so you can see. Whoops, I forgot my straight line. Here we go. Go back to your unit circle. Whether it's a handout or whether it's just something that you're remembering, and take a look at all of these angles on here. Find the points on the unit circle, and remember, the points are going to give you, the coordinates are going to give you the cosine of that angle. That'll be the x coordinate on the unit circle, and the sine of that angle. So this was cosine x, sine x for some angle x. There we go. So go back to your unit circle and go ahead and just fill this chart out. You can do it for the sine function first and then the cosine function or whatever you want. I'll let you pause the video and just figure that stuff out. All right. Here it is. So I've got everything plotted. So we've got, for the sine function, all these y values, 0, half, root 3 over 2, 1, root 3 over 2, half, 0, and then it dips into the negatives and goes back to 0. And with the cosine function, it starts at 1 because we're over on the x value, and then it goes over to 0, counts back down to -1, counts back up to 0, and then up to +1. So what we're going to do is we're just going to graph these points. So I'm going to start with the sine function. Here are all the points that we're going to plot, so we can look at each of these pairs as coordinate pairs where we have an x value and a y value, and you can just start plotting those things. So we've got 0, 0 right here, pi over 6 and half right here, root 3 over 2, you can say root 3 is bigger than 1, so root 3 over 2 is somewhere up here. And then at pi over 2, we're up at 1, etc., etc., etc. So go ahead and just plot those points, and you'll get all the points in this first spot here. Again, I'm going to pause the video and let you do that. This is what it should look like. So from here, it's pretty easy to just connect the dots. We can see we've got this nice curvature going through here, where it kind of waves up and down through our points. And then you might remember that we said sine is odd symmetric, meaning we're going to get a rotation through the origin, or you could say we can flip it horizontally and vertically. So it's going to end up looking something like this and start curving backwards here. Oops, I missed my spot. You can plot those points and go back through the negative angles, etc., etc., and you're going to end up with something that looks like that. But let me go ahead and show you. So here's us connecting the dots, and there's the nice reflection that we have. So because of the fact that our sine function is odd symmetric, we can get this shape here. So this is what our sine function looks like. It's this nice curve that starts at the origin And then we have this nice point at pi over 2, 1, back down to the x-axis at the angle pi, or if you want, you can think of that as 180 degrees, down to -1 at 3 pi over 2, or you could say that's 270 degrees. So maybe I'll write these. That's 90 degrees, 180 degrees, and 270 degrees, and then back to the origin right here. 360 degrees if you want. And then we could keep going and going and going, but at that point we're circling around the circle, the unit circle multiple times and all that kind of stuff. Cool. So there's our sine function. Our cosine function is going to be pretty similar. I'm going to go ahead and do this one in a different color. We've got these filled out, so this one is actually going to start up here. And then root 3 over 2 we said was pretty big. It's close to 1, but it's a little short. And then pi over 3 is at half, so that's going to be like here. And then pi over 2 is at 0. 2 pi over 3 is at -half, etc., etc., etc. And if you fill all those points out, you should get that. And I'll let you do that. Make sure you can actually plot all those, and you should get this shape. Once we've got that shape, we can connect the dots pretty easily. And we can see this nice, smooth curvature, if I could draw it correctly, that goes through everything and looks something like that. So there's the actual version of it. And then again, we can think of some symmetry. We said the cosine function was even symmetric. That means it's got this reflective symmetry. So that means points are going to get flipped over the axis. So when we fill out the graph, it ends up looking like this. We have this nice reflection across the y-axis. So those are our sine and cosine functions. It's a nice wave. And again, we can think about these points at 0, pi over 2, or 90 degrees, pi, or 180 degrees, 3 pi over 2, or 270 degrees, and 2 pi, 360 degrees. And those are these points right here. So if you can remember those ones, it's easy enough to remember what's going on. I always just think this one has a y-intercept of 1, though. So we got to talk about some properties of these functions. If we can figure out some properties of these functions, then we can be able to describe everything pretty easily. We know what the graphs look like, and here are some basic properties. The domain of both of these functions is -infinity to infinity, just like we thought of before. We said we can use any angle here for our sine function or for our cosine function. Maybe I'll say this is sine theta, and I'll say this is cos theta, just so we can keep in mind these are functions where the inputs are angles. Our range is -1 to 1. We said that that was the case by the unit circle, but now it's easy to see if we look at the graphs. Let me go back to our sine one. You can see very easily our biggest y value is right there, and our lowest y value is right there. That's not a very good drawing, but you can see it's going to be existing between -1 and 1. And the same thing is true for our cosine function. It's going to exist between 1 up here and -1 at its smallest. So our range is inclusive between -1 and 1. We've got those square brackets. The period is 2 pi, and that's because, again, as we go all the way around our unit circle, it's going to end up repeating after that. Or if you want, you could think of this graph, and we could cut this into some pieces, and we can say, maybe I'll use blue for that. We can say this piece right here is the exact same thing as this piece between 0 and 2 pi. Those pictures are the same. And if we go back to our sine function, it's the same thing here. This picture between 0 and 2 pi is exactly the same. Now, you could do this wherever you'd like. You could start anywhere and then just go 2 pi over and cut it up, and all the pieces are going to look exactly the same here. So the pictures in between these blue lines are identical. And the same thing on our cosine function. So the period here is 2 pi because that's the distance in between these lines. Our amplitude is 1. Have we talked about amplitude? I don't remember. Amplitude is just going to be the distance from the x-axis to the most extreme points. So maybe I'll write this down. Amplitude is the distance, we'll say in absolute value, so no positive or negative, we don't really care about the sine, from the x-axis to the farthest point. So since our range is -1 to 1, the amplitude is going to be 1 because we go from 0 up to 1 or from 0 down to -1. So the distance here is 1. And the same thing here. I don't think we've talked about amplitude before. But anyways, that's what amplitude is. Amplitude is the distance in absolute value from the x-axis to the farthest away point. It makes sense to talk about for a sine and cosine function. Amplitude, then, I'll use orange for that, is this distance right here. Or this distance right here. Same thing. It's the distance from the x-axis to the farthest away point. And for our sine function, we can do the same thing. It's right here. It's that distance, or it's this distance here. So those are some basic properties of our sine and cosine function. Well, why do we care about things like period and amplitude and all that kind of stuff? Well, it's because these sines and cosine functions are really nice by themselves, but what we can do is transform these things. So we have a list of different transformations. Let me see if I can type this nicely. Our transformations. We can do a shift. We can do that horizontally or vertically. We can do some sort of a scaling factor. Sometimes people will call this like a stretch or shrink. And again, we can do this horizontally or vertically. So if these are our transformations, what we want to do is figure out how they're going to work with these sine and cosine functions. So if you want to remember how to shift things up or down or left and right, you remember you're going to be doing some addition and subtraction in your functions. And for the scaling, we're going to be doing some multiplication on our functions. For horizontal stuff, it's adding and subtracting or multiplying stuff on the inside of our function. So maybe I'll just put this over here in yellow. I'll say horizontal. Oh, yellow is a bad color to use because I can't see what I'm typing. Maybe I'll use red. There we go. Horizontal is all going to be inside the function, and vertical is all going to be outside the function. So hopefully that's enough reminder of what's going on with these transformations. If it's not, I do have a little recap on Canvas, so I encourage you to check that out. This is stuff from algebra that we should try and remember. So if you can see it, great. But this is what it looks like for our sine and cosine functions. So we can see we've got some scaling factors on the outside and on the inside, and we have a horizontal shift. Notice here, I'll just write this really quickly, there's no vertical shift. That's pretty common. I'm having a hard time typing today. That's a pretty common thing in the way that these are presented in textbooks. Mostly because when we model these functions to like fit some sort of a situation, we want them to be going through 0. We want to have some positive and negative stuff. If for whatever reason you don't want to, you can shift things up or down. It's just not as common. But I think there's a couple that show up in the homework where you can do that. And you just add or subtract a number on the outside and it works out the same way that you'd think. So it's pretty typical to not see a vertical shift. We don't have a fancy name for it or anything like that. But what we can think about is that if we are applying some sort of a, I'll do this in blue, some sort of a vertical stretch, I'll just say vertical scaling because it could be a stretch or a shrinking, that's going to impact our amplitude. So our amplitude here is going to be 1, our normal amplitude, times whatever vertical shrinking or stretching we have, which we're writing as A here. So our amplitude is just A on both of these. Our period is going to be impacted when we stretch or scale things horizontally. We're going to stretch out the distance that it takes to start repeating, or we're going to compress that distance. And so that's going to be impacted by this B factor here. So B is going to be like our vertical scale, but you might remember, or sorry, our horizontal scaling, but you might remember that that's all reciprocal stuff. So 1 over B is actually the horizontal scale. stretch or shrink. Maybe I'll put that over here on the vertical one too, so we don't get confused by what I mean here. Stretch or shrink. So with horizontal stuff, you might just remember that things work backwards, right, than what we normally think. So that means our period is actually going to be divided by b. So our normal period would be 2 pi. So the period of these transformed things is 2 pi over b, whatever b is. And then you also might remember that when we shift things horizontally and scale them at the same time, we have to factor out the thing on the inside. C is not our horizontal shift. C over B is. And so that's what we'll do here. We'll call that a phase shift. When you shift the oscillating function left or right, we call that a phase shift with trig stuff. So this is just a horizontal shift. Maybe I can write that over here. Horizontal by C over B. And you remember that minus means right. Positive means left. Again, it's kind of backwards of what we think a lot of times. So just keep an eye on that. So if you've got a minus, that means we're shifting this thing to the right. And if you've got a positive, that means we're shifting this thing to the left. There's a lot to keep track of here, but honestly, I think it's mostly pretty reasonable if we remember transformations of functions from algebra. So if you're having a hard time with this, go back, take a look at that Canvas recap, maybe crack open an old algebra book or look up some stuff online and see if you can remember how those transformations of functions work. And then we can go back to our basic cosine function and our basic sine function and just apply those transformations. So let's do that really quick. So here's an example. I might just let you start with this. Maybe try and rewrite it. Notice we've got to do some factoring here on the inside. So go ahead and do that. Try and identify what your amplitude and phase shift and period and all that kind of stuff are, and then we can start graphing things from there. So I'm going to let you pause the video and start figuring this out, and then I'll just start cranking some stuff out. Go. All right, so really, this is 3 times cosine of 2 times x minus pi. Oops. Over 4. There we go. So we can see our amplitude is 3. What that means is that we're going to go between -3 and +3 now. We're going to stretch this thing vertically. Our period is going to get divided by 2. So this thing is actually just going to be pi now. Maybe I'll write this here. It's our normal 2 pi divided by 2 coming from this. And so it's just going to be pi. And then our phase shift, I'm going to put direction in here just so we can figure this thing out. We're going to shift this thing to the right because we've got a minus sign, and we're going to shift it by pi over 4. So what that means is that if we go to draw this thing, right off the bat, I'm going to go ahead and label this as 3 and -3. For the cosine function, we know it normally would start with a nice little y-intercept up here, but instead we're going to be shifting that to the right by pi over 4. So maybe I'll say, here's pi over 4, pi over 2, pi, etc., etc., etc. And I'm going to start here now. So there's my first point. Notice it's shifted to the right from where we normally would have it right here. Let me get rid of that so we don't have the ghost of that point flying around. Then you can think about x-intercepts. That's normally what I would do. Our normal x-intercept, or maybe I'll say our normal cosine function, the period ends up looking something like this, right? And so halfway through, it's at the negative amplitude. So we'll say like -3, and then it goes back up to 3. So normally, this would be like pi units away. So it's not at this spot, actually, because our whole period is 2 pi. But we've divided that by 2 now. So really, what we're going to say is that, oh, and this is wrong. My scale is all messed up. This is supposed to be 3 pi over 4. There we go. So what we're going to notice is that normally we'd go pi units over to get down to this -1, but now, since our period is pi, we're going to go half that distance to get down to the negative point. So we're really only going to be going pi over 2 units over. So if we're counting by pi over 4s, we're going to be down here. And that means our x-intercept is at pi over 2. It got shifted over by pi over 4. And if it was compressed, it would normally be at pi over 2. So then it gets compressed down to pi over 4 and shifted back over. And then we have another one here at 3 pi over 2, pi. There we go. That's 4 pi over 4. And then we've got one here at 5 pi over 4. And we can go back up to there. So our cosine function, maybe I'll use a red color for cosine. It's going to look something. Ooh, that's not great, but oh well. Something like that. There's one period of it. But then what we can do is just keep going because we know we have this kind of repeating behavior. So if there's negative pi over 4 and negative pi over 2, negative 3 pi over 4, etc., 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 we're just going to keep doing this same sort of behavior. Point there, point there, point there, point there. And then connect the dots. So there's our cosine function. Now, if you're having a hard time with this, what you can do is just graph this function using some technology as well and double check those points. What you'll want to make sure that you can do, though, is identify all these features and then see how things go from there. So one of the things to notice is like the domain is still negative infinity to infinity, but now the range has changed. Since our amplitude changed, our range now goes from -3 up to 3. The domain is still negative infinity to infinity because we can still put any angle that we want into this thing. But since we've stretched this thing vertically, our range changes. So that might just be something to like keep an eye on, right? Make a note of the fact that this range is suddenly a little bit different. So that's an important thing to see. Go ahead and do the same thing with the sine function. Notice that I've put a negative out front here. What that means is it's going to flip your sine function upside down. So there's a couple of things going on with this. Keep an eye on that. I'll let you play with this one. Pause the video and come back, and then we'll kind of go from there. All right, so if you're back, if you've done this already, I'm just going to rewrite this. This is -2 sine of half x plus pi over... Oh no. Did I do something wrong? No, I'm okay. Sorry. I got all in my head. All right, I'm all right. I thought I was going to have to re-record this video, all that stuff. Anyways, looks like this. So if we multiply all that stuff through, we get x over 2 plus pi over 4. So we can see there's some shifting, there's some scaling, all that kind of stuff. Our amplitude here is not -2. It's just 2. Because we're looking at an absolute value of this, we just care about that distance, so positive or negative doesn't really mean anything. Then what we might want to talk about is the period. For the period here, we're going to look at our normal period divided by this value right here. So it's really 2 pi over half. When you divide by half, that's really multiplying by 2. So this is 4 pi for our period. So we're really going to be stretching this thing out this way. And then we have this phase shift going on. And our phase shift is going to be shifted to the left because it's a plus sign by pi over 2. So left by pi over 2. So hopefully you got all that stuff. Now what we're going to do is draw our graph. Oh, that's not very good. Let me move this. I'm going to do this right here. And I'm going to go right through the middle. All right, so I'm going to go ahead and put little tick marks up here at 2 and -2. And normally our sine function starts at the origin, right? Which is kind of nice because when we stretch that, it doesn't really move. And when we stretch it horizontally, it doesn't really move. But we are going to shift this to the left by pi over 2. So let me just mark pi over 2 right here. And now we've got our point. That's where we're like starting our sine function. Now, normally our sine function goes up from here, right? Normally we'd end up looking something like this, blah, blah, blah. Since we have this negative, it's actually going to get flipped upside down. So this is a little bit weird. Then we can also say normally halfway through the period, we'd cross through the x-axis again. So halfway through the period, we have another x-intercept. Our period is 4 pi, so what we're going to do is we're going to count up to our by 2 pi from this starting point. So here's pi over 2. Here's another pi over 2, so we've counted up pi distance away. That's 3 pi over 2 distance away, and at 3 pi over 2, we're 2 pi distance away. I know that sounds weird, but we're thinking about these in terms of halves of pi, right? So there's a half of pi, 1 there. There's 1 pi now, 1.5 pi's, 2 pi's. So this is our other x-intercept. Then halfway through here is when we're going to end up crossing or having our kind of max amplitude. Normally that's at pi over 2, but we're going to end up shifting stuff and things like that because normally that distance is pi from here. But now it's 2 pi. So what we're going to do is we're going to say this distance, sorry, is 2 pi. So half the distance that we're looking at is pi. That's going to be right here. It would be here normally, but we're flipping it upside down, so it's actually going to be down here. Then we can start kind of thinking about connecting the dots, but let me draw more over here actually. Let me go up to 2 pi. And let me do one more maybe. So that's 4 pi over 2. So this is 5 pi over 2. So this one is going to be our point up here. And just for fun, I'm going to kick in a couple more over here. So this is negative pi. This is negative 3 pi over 2, etc., etc. And that's going to be up at this point. And so here is this sine function. Oof, that's really bad. My scale isn't perfect. You see how these are farther apart than these ones with my tick marks, so it looks a little stretched. But this is a sine function that gets really horizontally stretched, and then we just have to shift some of these points around. So again, I always just think about where's that first normal starting point at the angle 0, the x value of 0, going to be, and then move it from there. Hopefully, those are some things that you're seeing. This is a function that you're graphing. Again, I only really focus on those ones that I was circling before, the x-intercepts and then the peaks and the low points of our functions. All the stuff in the middle, the x value or the y values of like half and root 3 over 2, I kind of just skip those, to be honest. You can put them in if you want, but they're a little harder to mess with. I think as long as you get those main points and you know the shape of the graph, everything else works out pretty nicely. So the last thing that we want to talk about then is modeling periodic behavior. So there's tons of examples of things that move periodically. And when I talk about periodically, we just mean like they have this like cyclical nature, right? Where once you understand one time window or something like that, it keeps repeating. An easy one is something like every year has 4 seasons, and they kind of act in the same way, and they change seasons around the same time. And so we have this nice oscillation between, summer, fall, winter, spring, summer, fall, winter, spring. We keep bouncing around between those things as time marches on. Other classic examples are things like the tide. If you go to the shore of an ocean and the tide comes in, the water level will raise up. And then when the tide goes out, the water level will drop down. And then when the tide comes back in, it'll raise up and go down and up and down. And it happens consistently in the same kind of way. So it happens periodically. So the main idea is if we know the amplitude, the maximum height, I guess, of this thing, and the maximum lowest point of this thing, and the period, then we can start building a sinusoidal function. Sinusoidal just means like sine or cosine, this nice wavy oscillating shape. And then if we can model that really nicely, we can do some stuff. So then phase shifts and vertical shifts, what do? Well, a phase shift is just going to change where our function crosses at 0. So that's a really important thing that can change depending on what you make 0. and vertical shifts can change that from 0. So like, for instance, if we're thinking about like a water level, our water level with tide coming in and out is never actually going to be negative. So what we might do is we might take some sort of a function that looks like this and just shift it up so that it looks like this instead. And so we have some sort of like a consistent water level, and it's never really negative, although my picture's bad. So we can shift things vertically. And then the question is, well, how do you know which one of these to use, sine or cosine? And the answer's kind of nice, but also terrible. It doesn't really matter. You can use either one. But we might notice that some of them are more obvious to use. For sine, we'll remember that this thing goes through the origin. And for cosine, we'll remember that this thing starts at its max height. And that's pretty much it. So if you have something that starts really big, maybe use the cosine function. If you have something that starts right in the middle, maybe use the sine function. But we've already seen that you can shift these things to get the other function. These functions are just horizontal shifts of each other. You might remember that sine of x minus pi over 2 is cosine of x. That was that the complementary angles or the cofunctions or whatever. We have this identity already going on. These are just horizontal shifts of each other. So here's a really nice example, I think. This is another periodic one. I actually just looked up all these things so we can model this. So the number of hours in a day in Chicago is periodic. Our days are long in the summer. They're short in the winter. And in between, they kind of just keep fluctuating. And they do this in a consistent way that we can easily model. Our longest day is 6 hours longer than the shortest day. And the median hours of daylight is 12. So that means our max is 18, and our, oops, sorry, not 18. It's 3 more than 12, so it's 15, and our minimum is 9. So the longest day that we normally see is 15 hours of sunlight. The shortest day is 9 hours of sunlight. The longest day of the year is summer solstice, June 21, but I'm going to say that's 171 days after the first day of the year. So what we're going to do is we're going to say X is the day of the year, so it's the number of days. Oh, that's supposed to be after. I forgot an R here. There we go. January 1. So X equals 0. That's January 1. X equals 1 is January 2. X equals 31. It would be 31 days after January 1, which I believe is February 1st. So June 21st is 171. So what we want to do is write a function that models all this. So we know our longest day is at June 21. Let me just clear all this stuff out. So since we've got information about our longest day, maybe it's helpful to use the cosine function because we have some information about where the peak is going to be. So we can think about this as like a cosine function that's shifted. If the peak is at 171, then maybe what we have is like a cosine of x minus 171. Right? Because now, instead of our peak being at 0 for x, it's at 171. If you put 171 in for this, you're going to get cosine of 0. That's the high point. So our longest day is going to be right here. So that might be a nice thing to think about. So we might have this cosine of 171. You might also notice that the amplitude of this thing is going to be 3. We've got this, maybe, you know what I'm going to do? I'm going to get rid of a bunch of stuff, and I'm going to use the highlighter on here. I have a highlighter. I may as well use it. So we're going to say our longest day is 6 hours longer than the shortest day. That means that there's a 3-hour fluctuation between the longest day and the median day, and the shortest day and the median day. So our amplitude here is going to be 3. So let me just start writing some stuff down. So we know we're going to use the cosine function, because we know the high point. So we can shift our cosine function, and wherever the normal x value of 0 would be, if we shift that, that's going to be the high point. We do have a phase shift of 171 to the right, because the 171st day after January 1 is our longest day. So that's where that normal x value of 0 on the cosine function is going to be. And we also know that the amplitude is 3. Because again, our maximum is 15, our minimum is 9. We also have a vertical shift here. 12. That's because normally our cosine function keeps passing back and forth through 0. Obviously, it does not make sense for us to have 0 hours of daylight or negative hours of daylight, so we're going to shift all this up 12, and now we're going to bounce around between 9 and 15. We're going to go above 12 and below 12, and above 12 and below 12. So we're going to use the cosine function. We're going to use a phase shift of 171. We're going to use an amplitude of 3. We're going to use a vertical shift of 12, and the last thing we need is the period. The period of this thing is 365. Because this repeats every year. So we'll say 365 days. So what we have to do is figure out how to get 2 pi to turn into 365 by doing some sort of like division thing. So what we want to do, let me write this, is say 2 pi divided by something should be 365, because remember, whatever coefficient we use, we're ending up dividing our period by that. So what I'm going to do is I'm going to just be a little annoying, and I'm going to say the coefficient that we're going to use is 2 pi divided by 2 pi over 365, because now that's 2 pi times 365 over 2 pi. Those cancel out, and we're just left with 365. So our period needs to be 365, and so what that means is that our coefficient on this is going to be this 2 pi over 365. That's a little bit weird, right? What that really means is that in general, let me erase all this stuff. In general, the coefficient that you're going to use on the inside is going to be the normal period divided by, maybe I'll write this, normal period. So it's 2 pi for us, divided by the period we want. Let me do this. Divided by, oh, look at that. I'm actually going to stack them on top of each other. So for us, our coefficient is going to be 2 pi over 365. And so we can go ahead and just write this thing. So this is going to be f of x equals amplitude of 3. So 3 times our cosine function of 2 pi over 365 times x minus, our phase shift was 171. Uh-oh, I'm running out of room. Let me rewrite this smaller. Sorry. So I'll say 3 times our cosine function of 2 pi over 365 times x minus 171 plus 12. There's our vertical shift there at the end. That's just going to bounce this thing up. If you want, you could go ahead and do this multiplication through here, and you'll end up with 3 times cosine of 2 pi over 365 x minus 342 over 365 pi. I don't know what that is. You could reduce that if you want. Plus 12. I'm going to write that plus 12 down here. There we go. So that works out pretty nicely. I don't know if you can actually reduce that, so maybe I'm wrong. That works out pretty nicely, though. There's your weird function, but this is going to model the number of hours in a day in Chicago. So now if I told you, let's take a look at the number of hours in a day in July 5th, I don't know. We just need to know how many days after January 1st that is. That's an easy thing to look up, and you can plug that in for X, and that'll give you an approximation of the number of hours a day in Chicago. So that's pretty cool. So these applications are a little bit tricky, but try and focus on labeling through this kind of business here. And that should work out pretty nicely for us. Once you've got all that, you can put everything in place and get some really cool functions that do some really cool things. All right. Good luck with all that stuff. Let me know if you've got any questions.